Raw query counts can expose the one person who searched a rare phrase. OpenDP bounds each user's contribution and adds calibrated Laplace noise before the analytics leave the log store. You'll publish noisy, approved query category counts with per-user contribution caps and an explicit epsilon budget using OpenDP. I'm Professor Pi, teaching search and IR with simple Python. Search logs are useful because they show what people need. A retrieval team might see demand for billing, password reset, or product setup. But raw logs also contain private intent. A rare query can identify someone even when the user ID is removed. Differential privacy gives us a safer way to answer the useful question without publishing every person's exact behavior. We will release category counts, not raw search text. Each user gets a limit, and carefully chosen noise hides the effect of any one person. OpenDP is a good fit because it makes the privacy rules part of the data pipeline. Instead of adding random noise by hand and hoping it is enough, we ask the library to check the privacy relationship for us. We will turn a tiny search log into a report of approved query categories. The key idea is simple. Only reviewed categories can appear in the result, so private free text searches never become public labels. Quick note, this code is designed to teach the core idea clearly. Library versions and local setups can vary, so check the official docs if your setup behaves differently. We first need a safe set of categories before we count anything. This snippet starts the report with a tiny approved category list and filters the raw log. Rare free text queries are the exposure point, because removing user IDs does not remove the fact that one person searched a unique phrase. The code enables OpenDP with dp.enableFeaturesContrib, then keeps only terms and cats, so the later report uses public, reviewed categories instead of arbitrary strings. The toy log stands in for search analytics events from a retrieval or RAG system. The output shows how many events remain after category approval, which matters because this is the safe input surface for counting. Now that unexpected phrases are gone, we can measure demand across the categories we approved. This example turns the approved search terms into a category histogram with OpenDP. The important shift is that hist only counts the categories and cats, so an unexpected phrase like a customer name is not turned into a public bucket. Input space declares a vector of strings with dp symmetric distance, and dpt.then count by categories creates the OpenDP transformation that produces one count per approved category. This is still an exact, non-private diagnostic step, so it is useful for understanding the shape, but not for publication. The output shows the unnoised demand pattern that the later private release will protect. Exact category counts are useful for development, but one frequent searcher can still have too much influence. This code caps how much any one searcher can affect the report. A single power user can otherwise dominate multiple categories, forcing more noise or weakening the protection story. Max terms is the per-user cap, and dp.unitOfContributions max terms records the privacy unit that OpenDP will use when checking the release. The short loop keeps only approved terms and stops accepting events from a user after the cap is reached. Increasing max terms preserves more behavior from heavy users, but requires more noise for the same epsilon. Decreasing it improves sensitivity while dropping more events. The output shows the bounded event count that feeds the private histogram. The cap protects the release, and now we should check whether it changed the practical story we want to report. This snippet checks whether the contribution cap changed the visible demand story. Engineers often care about the top failure modes, but they also need to know whether a leaderboard is being driven by a small number of users. Bounded exact reuses the OpenDP hist transformation on bounded, then max selects the current leading category. The variable drop is available for review if a top category loses events after bounding, which can signal that the raw count was too dependent on repeated contributions. The output shows the top bounded category and its count, giving a stable target for the private release. We have a bounded report now, but it is still exact, so the final step is to add privacy-preserving noise. This example completes the private release path with an explicit epsilon budget. The code asks OpenDP to find a Laplace scale with dp.binary search param, so the chained report satisfies din max terms and dout equals epsilon. Then, report combines the approved category histogram with dpm.then Laplace, and published holds the noisy counts that could be shared instead of exact. The noisy values are intentionally not printed here because OpenDP uses randomness for the release, while report.map max terms gives a stable budget check for the tutorial. The output shows the epsilon actually spent, which matters because privacy review needs a concrete ledger entry. This is the full safety story in miniature. Approved categories prevent accidental disclosure through labels. Contribution bounds limit any one person, and Laplace noise protects the final counts. The trade-off is accuracy, especially for small categories, where noise can matter more than a signal. In a real search system, run this report on a controlled schedule and record each epsilon release in a privacy ledger. Keep raw logs access controlled, publish only the noisy category report, and review category definitions before they enter the pipeline. Try changing max terms and compare the bounded exact leaderboard with a private report. You will see why contribution limits are not just a technical detail. They shape both privacy and the kind of search behavior your analytics can represent. If practical search and privacy lessons help, subscribe and watch the other IR videos.